Hello and welcome to part 6 of this tutorial. This is the last part, and this is a fairly short part. And what I intend to do in this part is to talk a little bit about how codes that are designed for multiple access can be used for solving compressed sensing problems. To put this in context, um, just to refresh your memory, in part 3 of this tutorial, we talked about how the unsourced multiple access problem is the same as a compressed sensing problem. Or we took a compressed sensing view of the unsourced multiple access problem, and using this view, we designed some divide and conquer strategies like the coded compressed sensing. And then in parts 4 and 5, we thought of this unsourced multiple access problem as a pure channel coding problem, or as designing codes for random access. And in the last two parts, I showed you some coding schemes which perform well for the unsourced multiple access channel. Now that we have this connection between unsourced multiple access and compressed sensing, in this part, we're going to see whether we can use codes that are designed for multiple access to design good compressed sensing schemes, sort of closing the loop in the connection between compressed sensing and unsourced multiple access. And that's exactly what I want to do. And there is a very nice compressed sensing application where this makes sense. And this is the problem of heavy hitters in data stream computing. So if you're not familiar with this problem, the problem is the following. Think about a router in a network. Suppose the router wants to count how many packets are flowing to any given destination from which sources. So in other words, it wants to keep track of saying, from IP address I, how many packets have flown to any given destination. And it wants to do this for every possible IP address, right? So we are really trying to collect a histogram of the packets that have flown through the router to a particular destination. Now the IP address space is huge. The IP addresses are, let's say, 64 bits, which means what we are really interested in is in collecting a histogram which has 2 to the 64 possible entries, right? So the ith entry here is the number of packets that have flown from the ith source to that given destination. And it seems like, and now if you want to store this information at the router, you can see that the amount of storage required is extremely large. Now, but it turns out that there is a small subset, typically there is a small subset of sources from which packets flow to a destination. And these are called as heavy hitters. In other words, even though 2 to the 64 possible sources could have been there, really there is only a very small subset, in this case K of them, which are likely to have packets for destination J. So the idea in heavy hitters is to store a sketch instead of store the histogram completely. So in other words, if you think of X as a vector which stores the histogram, what we know is that X is a k-sparse vector. So instead of storing X directly, what we try to do is we store a sketch of X given by Y, which is A times X, where A is a sensing matrix and A is of size N by 2 to the B. Obviously, N is much, much smaller than 2 to the B, right? And now you can see that this is really a compressed sensing problem. If you want to recover X, you can recover the heavy hitters in X by using a decoding algorithm for a compressed sensing problem. So this is a very nice way to save storage in these in routers, and it has been quite popular in theoretical computer science. Now, I should also tell you that there is a very nice way to implement this in practice too. Notice that we are interested in the histogram of the number of packets that flow through a router. And what we can do is we can create a running sketch. So in other words, every time you get a packet, you can look at the IP address. For example, if the IP address is the third entry here, then what you can do is you take the third column of A and you add it to your current sketch. So every time a packet flows, you would add one column of A to your sketch. So the sketch at any point has A times X, where X is a histogram of the number of packets that have flown um, through the router. Okay. Now, the problem or in implementing this is really that the complexity of decoding is very, very large if you're not careful about it. Because naively speaking, the sketching matrix is too large. It's of dimension n by 2 to the b. And of course, B is of the order of 64. So this is an extremely large matrix. It is so large that you usually do not even store the matrix, right? So you want to have a way to actually create the columns of the matrix on the fly, and you don't even want to be able to store the matrix. And this computational challenge has been addressed in the literature. There are many nice ideas, mostly from this theoretical CS community, and there are algorithms like the chaining pursuit, for example. It's a very low complexity algorithm. It has complexity which is only order of k times b instead of order of k times 2 to the b, which would be the complexity if you just used commodity compressed sensing solvers. So the idea in these algorithms is to enforce some structure into the sensing matrix A and use the structure to be able to design low complexity algorithms. There are a couple of other algorithms which can be used. For example, there is this peeling algorithm of Lee and Ramchandran, and this works in the regime where the sparsity is sublinear in the dimension, or it's sublinear in 2 to the b. And here, the complexity of this algorithm is only dependent on k, and as k is sublinear, then you get a sublinear time algorithm. So I'm not going to review all these algorithms in detail, but what I'm going to talk about here is to say that if we take the viewpoint that the compressed sensing problem is a multiple access problem, we can use codes that are designed for multiple access to solve this problem and you require far fewer number of samples or the size of the sketch, or n, which is the size of the sketch that you need to store, at a slightly higher computational complexity. So I'm going to just try to hit the main idea, given that we are towards the end of the tutorial, and also partly because this is a work that's in progress. So I think I will keep the description short, but here is the main idea. So the main idea is to go from the index space to the bit space instead of from the bit space to the index space, right? So if you think about the vector that we want to store, this is a vector which has 2 to the b indices. And what we'll do is for every index, we'll look at the corresponding bit representation, which in this case has a very natural interpretation. This is the actual IP address of the packet that's flowing through. So what you do is you take the IP address of the packet, take the 64 bits, and you encode it using a multiple access code. For example, the polar coding scheme that I described in part B. So this whole part is like a code that's defined for the multiple access channel. You can pick any code that you want. You pretend to be one of the users, and you simply encode it using a polar coding scheme followed by BPSK, and then you have the spreading sequence, and then you can spread it, and you won't transmit it in this case. You can add it to the current sketch. And then if another packet comes here, you do the same thing. You convert it to bits and you can encode it, but you can pretend, or you can think of it as another user being encoded. So the K heavy hitters that we have here, we can think of each one of those heavy hitters as one user. And in the end, the sketch that we have is actually the sum of the code words corresponding to all these things, which is actually exactly the same as the output of your multiple access channel. Now, the problem of recovering X, this vector X, from the sketch Y is the same as the decoding problem of decoding these users from Y, and which is exactly what we talked about in the last part. And so you can use this serial interference cancellation and minimum mean squared error detector to be able to solve this problem. I feel that this connection is quite nice, and to the best of my knowledge, this has not been explored in much detail, at least this viewpoint of thinking of using codes designed for the multiple access channel, particularly polar codes and things like this, for solving compressed sensing problems like this. Now, just there are a few minor differences between what we saw in part 5 and this problem, and I'll talk about them. The first one is the fact that we may not always have the same number of packets that flow to every IP address in the heavy hitter. So for example, the number of times we see this index may be different from the number of times we see this index. So what that means is that the number of times we add this code word to the sketch is going to be different from the number of times we add this code word to the sketch. But one way to think about it from a communication theory point of view is that you can say that this code word is multiplied by a fading coefficient. And this code word is multiplied by a different fading coefficient. These fading coefficients are of course integers, but nevertheless, we can think of a multiple access channel with fading instead of just a Gaussian multiple access channel without fading. And we have to make some adjustments to the decoding algorithm, and I'm not going to talk about them in detail, but nevertheless, you can do that. And one more difference is that typically in this problem, you're going to have K heavy hitters, but you're also going to have a few IP addresses from which packets are going to flow to any given destination. So these indices, they are not heavy hitters. These are the non-heavy hitters. And the non-heavy hitters are nevertheless going to be encoded by this kind of an encoding scheme, right? We're going to convert this to bits. We are going to encode this because we don't know while we are forming the sketch, which ones are heavy hitters. And so when you add it to the sketch, this is basically playing the role of noise. Although it is not Gaussian noise, and you can see that the interference also comes from exactly the same code book that we used to encode the heavy hitters. So there is a little bit of structure in the interference here, but if the number of packets that flow from the heavy hitters is much larger than the number of packets that come from the non-heavy hitters, we will see, I mean, our simulation results show that, you know, this algorithm still works. So I'll start by just showing a quick simulation result. And like I said, you know, this is work in progress. So this is very preliminary results. This is not something that's very complete. But here is an interesting result. So in this case, we had 25 heavy hitters and 1,000 packets that flew through the router. And we assumed with 40% probability, you would pick one of the 25 heavy hitters. And I believe the IP address space was pretty large. I am not 100% sure exactly what it was. I think it may have been something like 12 bits or 16 bits, somewhere in the thousands. And you can see that the number of measurements, actually I take that back. I think the IP address space was much larger. I take that back. So when you plot the number of measurements on the x-axis and you look at the best k-term approximation on the y-axis. So what we are doing here is we are reconstructing it from the sketch and we are comparing it to the true value, and then you are observing what the error between the reconstruction and the true value is. Actually, we look at the best k-term approximation to the true vector, and you take the error between our reconstruction and the best k-term approximation. And you can see for the same best k-term approximation, the number of measurements can be substantially smaller for our scheme. In fact, you know, this curve basically remains flat like this. So compared to the black curve, which is chaining pursuit, the polar coding scheme seems to perform extremely well. The flip side, of course, is that this is a little more complex. This is more complex than this, but what you gain is in terms of number of measurements required. Okay, so most importantly, I'm kind of excited by this idea of using codes that we more or less designed for just multiple access channels, right? And it seems that these could be used for constructing sensing matrices for large scale compressed sensing problems, where you get to choose the sensing matrix. So keep in mind that here we're in a situation where this A is entirely under our control. So I think I'll stop here.